Berkeley before taking up a tenure-track position at Harvard Med College in Claremont, California. Shortly after gaining tenure at Harvard Med, she moved to the Kirk Lecture, University of South Australia in Adelaide. Lesley is a very active champion of increasing the participation and recognition of women in all areas of mathematics and science. She set up and sponsored women in STEM associations at Nuffield and 5 different universities, and she's organised a number of key conferences championing the work of women mathematics. She's a recipient of numerous awards and distinctions. For example, she's fellow of the US Association for Women in Mathematics, and also the Australian Mathematical Society. And of course, she's our Kirk Distinguished Visiting Fellow as well. Her research is in harmonic and complex analysis, and today she's going to talk to us about Fourier, harmonic analysis, and spaces of homogeneous type. So thank you, Lesley.
Thank you, Linda, for that warm introduction. I'm delighted to be here at the Newton Institute for this complex analysis workshop, or a large part of it, and I'm honoured to be a recipient of the Kirk Fellowship. Thank you. Thank you all for coming today. I'm looking forward to sharing with you something of a whole research program, and as you'll see, there are several different themes embedded within it, but I would just like to acknowledge some of my many co-authors and the support of the Australian Research Council, which has funded some of this work. And the first of these themes is about building what's called a Calderon-Zygmund theory of functions. I'll introduce you a little later to Calderon and Zygmund and what they did. And defined, but the key new the key new point here is that our functions are going to be defined on some mysterious red triple here, which I will also explain later. And these are the so-called spaces of homogeneous type that are in my title. So the talk is in 3 parts of somewhat different lengths. Something about Fourier, Fourier theory, and a little about his fascinating life. If you don't already know about Fourier's life, you will just be amazed, I think. And I will not have time to talk about much of it either. Harmonic analysis is the part of mathematical analysis that grows out of Fourier series, the Fourier transform, and has led in many, many different directions, including more recently the study of functions and different properties of functions, and that is the part that I work in now. And then spaces of homogeneous type I will come to as a new domain on which these functions can be defined. So as an outline of the talk today, a bit about Fourier and harmonic analysis, an introduction to the Calderon-Zygmund theory, an introduction to the spaces of homogeneous type, with quite a lot of pictures through most of this part, and then a somewhat more technical part talking about extending the Calderon-Zygmund theory to this new setting. Now, I found I couldn't confine myself to just one theme, as it turned out, so I identified 3 in the end. The one that I advertised already. The second is that when we talk about functions, we often want to know something about their regularity. How smooth are they? Are they continuous or 5 times differentiable or what? And you can often capture that information by the size of some coefficients you compute for that function. And those could be Fourier coefficients, or these days they could be wavelet coefficients or some other kind of coefficient. So that's one of the themes. I will try to point that out here and there. And finally, given the nature of this program, I want to point out some of the many, many links between harmonic analysis and complex analysis as well. So I won't have time to say all of the ones that are secretly there, but some of you will spot some, I'm sure. Harmonic analysis begins with Fourier, Jean-Baptiste Joseph Fourier, who was born 2 years before Beethoven in 1768. That made him 20 or 21 when the French Revolution broke out, and he lived through some extremely turbulent times. He died at about the age of 62, but until then, as I may have time to say, he escaped a number of difficult situations, sometimes by the skin of his teeth, and these were political, financial, military, imprisonment, and a whole range of other difficult academic circumstances as well. So we will come to some of that. Just on the mathematical front, at different points in his career, he was taught by Lagrange, Laplace, and Monge. He was a colleague of Monge and Lagrange, and he succeeded to Lagrange's chair at the École Polytechnique. Among his students were Poisson. He wrote the eulogies for Delambre and Laplace, and later in life he was a close friend of Navier-Stokes, who inherited Fourier's papers after his death, and also of Dirichlet, Liouville, Sturm, and Sophie Germain. So just on the mathematical front, he lived in interesting times and was very broadly connected. The first problem that he studied and reported on in detail in the area of the propagation of heat was this one. Imagine that you have a half-infinite strip. So this strip has a fixed width. It extends to infinity in that direction. It has some fixed width. It doesn't extend in that direction, and it's very thin. It's very thin. It's sort of effectively almost one-dimensional. Two-dimensional. It's a flat thing. And so you can coordinatize that by having the side of finite length run from, say, x equals -1 to +1, and then set the infinite direction going up towards infinity that way. And Fourier was interested in predicting the temperature at different points in this plate. So any point in that plate you can think of as having a coordinate. In these coordinates, x, w would be the names of the pair of coordinates. And Fourier solved two problems in his analytical theory of heat for this. He solved the problem that says, let's keep the edges at certain fixed temperatures, and from that predict the temperature at any interior point, xw. So the initial temperature conditions he chose for himself, the first set of boundary conditions, were to, along this short end of the strip, keep that constant at a temperature of, say, 100 degrees by applying heat to it continuously and keeping it at that temperature. And then along the two semi-infinite rays that are the two long sides of the strip, we'll keep those fixed at 0 degrees by packing them in ice or whatever. And so with those boundary conditions, you want to be able to calculate the temperature at any interior point after it's equilibrated. So there's no time in this first problem. The second problem he put in was, well, how does it come to equilibrium? So to add the time dependence, where you might start out with those boundary conditions, and then it takes some time with temperatures going up and down inside until it comes to equilibrium. So Fourier also formulated and solved that problem. And in doing so, he derived from physical principles the heat equation. If U is temperature, then du dt equals uxx plus uww in those coordinates, and the two second derivatives with respect to x and with respect to y added. And that is the time-dependent heat equation. And the steady-state version is when you set the ut equal to 0, so it's Laplace's equation. And so he derived those from physical principles. And also, he invented a method of finding analytically formulas for the solutions to both of these versions of the heat equation. And what he says about that in his introduction to the book that I have cited here is, the equations of heat conduction, like those of sound or small oscillations for liquids, belong to one of the most recently discovered branches of science which it is most important to extend. Having established these differential equations, the heat equation and so on, we must obtain their solution, which involves passing from a general to a particular solution, obeying all the boundary conditions. This difficult investigation requires a special calculus based on new theorems, which was his method of separation of variables and Fourier series. The method which results leaves nothing vague or undetermined in the solutions. It leads us to the point where we can obtain numerical values, a necessary property of any such method. So he's touched on quite a lot of the themes of our workshop, I think, in the introduction to Théorie analytique de la chaleur. He wasn't necessarily the first to have thought about these sorts of problems, but he made enormous advances in the subject. So the main idea, which my colleague Christina and I feel is so important that we put it on the cover of our book, in this picture, which I'm not sure how well you can see that from where you are. But the main idea is that you are going to break your generic functions of time, say, or of space, into sums of simpler building blocks. And so the first example I want to show you is this middle line on the cover of the book here. And what you can see on the left is a kind of doubly wiggly line. And so what that line is doing, from your point of view, if you follow my hand, it's doing something like that. But how do I make that motion? What I'm actually doing is one motion with my elbow, a large, slow cosine wave, and another motion with my fingers, a small, fast cosine wave. And if I do those both at the same time, let's see how coordinated I am, then you can see resulting the full picture of the graph that you see written here. So physically, that's what's happening. We're superimposing those two waves, or adding them. And here is the formula for f of t. So we're thinking of t as the time variable increasing from left to right. And the amplitude at any particular moment, the height above or below the middle rest position, is given by this combination, 3 times cosine of t plus 0.5 times cosine of 16t. So the first of those is the large, amplitude 3, slow oscillation, and the second is the small, amplitude 0.5, fast oscillation with a faster frequency. That's it. Now, in practical terms, let's say you wanted to send the picture of that graph as an image to someone else. So you could plot or record for each pixel along that way the height, the corresponding height. And that would give you a long list of numbers, in fact, a long list of pairs of numbers. Or, if you knew the code, you could send the numbers 3 and 0.5 associated with 1 and 16, respectively. So obviously, there's signal processing advantages here. What if you had a different type of signal? These first ones are Fourier sines and cosines, and this is a very simple example of a Fourier series. The individual cosines in this case are called harmonics. What each of them for a given fixed frequency like this 16, expressed in that 16, what each of them corresponds to is a pure tone at a single note, as if you played middle C on the piano or A on the violin, you would get a particular frequency note, just one of these cosines. Hence the name of harmonic analysis. But if we moved on to other types of functions, such as this one here, which again has a large, slow oscillation, but is not as smooth. This one has corners and jumps, and which is interrupted by some sort of small, fast oscillation, but only for a short time. It turns out that sines and cosines are not always the best adapted building blocks to use for a signal of this type, and many practical signals are like this, for instance. This could be some audio signal with a burst of static in it. And so it has proved useful to use different sets of building blocks, including the so-called Haar wavelets shown here. So a single square wave, which, and what you can't see, is just compactly supported. It's just got one down, one up, and after that, it doesn't oscillate anymore. And the same for this little one. So these types of wavelets, which instead of being supported on the whole line, like sines and cosines, are compactly supported, and which can be built to have more smoothness, if you want, turn out to be extremely useful for lots of practical situations. The same idea, though. You have particular Haar wavelets associated with particular intervals, so that might be I2, I1, and this little interval here might be I2. And then you have coefficients that, so what tells one function apart from the other is the list of its coefficients with respect to the given basis. And as I hinted before, the size of those coefficients will tell you something about what type of function you had. So here's an actual audio signal of a voice over time, over about 5 seconds. And this is the amplitude, normalized amplitude on the vertical axis of the signal. And this voice is saying, and you can probably pick out some of the words or phrases, "Hi, Mum, it's Amanda, and I can't wait to tell you what happened today." So that's a recording actually of me. So a friend from engineering helped me to record this and display it, saying that. And you can see it's possible, well, we have got these sort of short burst things we don't want to waste a lot of our sines and cosines coefficients adding up to places where the function's almost constant, like there. And it turns out wavelets are pretty well adapted for analyzing this type of signal. And without going into much more detail, I'll just say this application to signal processing, what that actually means is you speak into your phone and it records the kind of, it's taking in the analog of the movement of the air pressure. The air is moving as you speak. It converts that into some sort of a list of numbers, possibly amplitudes and frequencies. It compresses them, perhaps by thresholding, by throwing out all of the coefficients where the amplitude is less than 0.1 or something like that. So you just keep the big amplitude bits of the signal, and then you might just send that shortened list, and at the other end you have another algorithm that puts them back together and recovers from the amplitudes that you sent and the frequencies that you sent, that recovers the signal. So that works for sound signals, and it also works for images. This is how a photo you might look at on the web is stored out there in the cloud and comes down to you by some sort of version of this. Here are a few of the other applications of harmonic analysis, and it's sort of hard to find another area of mathematics that has had so much impact in the practical world in engineering and science. I'm not going to have time to talk about many of these, in fact extremely few, but I will mention the JPEG 2000 image standard, which uses both discrete cosine Fourier type methods and also wavelet methods for storing, any photo that you have which has a suffix .jpg is stored according to that standard. So you're using harmonic analysis every day. The fast Fourier transform is a way of quickly computing Fourier coefficients. And Cooley and Tukey's original paper on this is extremely short, but also one of the 10 most highly cited papers of all time. Some of my other personal favorites are the age of the Earth, which determination of estimates of the age of the Earth has a long and tangled history in which Newton plays a part, and so do many other people like Kelvin, Buffon, and so on. Newton's part was he suggested, well, things cool down, right? So what if the Earth had been made of a sphere of iron? He knew there was lots of iron in the Earth. He suggested this kind of thought experiment. If we could measure how quickly a sphere of iron cools down from an initial temperature, then we could posit an initial temperature and work out how long it would have taken to cool to its current temperature, and that would give us some sort of estimation of how long the Earth has been. That was his idea. Of course, he never did it because it's ridiculous. But guess what? Buffon, of Buffon's needle problem, did a set of ridiculous experiments with metal spheres of various sizes and various metals. And he had these two metrics of, we're going to see how long it takes to cool down to the point where you can keep your finger on it. So it doesn't record whether it was him or his assistants who had to do the part where you keep your finger on it. But anyway. And part of Buffon's theoretical underpinning for this you can address using methods of Fourier series and Fourier theory to actually calculate from his temperature cooling data an estimate for the age of the Earth. Kelvin built an actual machine called a harmonic analyzer. In fact, he built two such machines. One of them took in old tidal data and modeled it with a Fourier series by finding the Fourier coefficients. Another one actually took in old data but predicted future tides. So extremely important for a lot of reasons. And the last one I'm going to mention is electroencephalograms, which are when people put electrodes on your head to measure your brain function. And it turns out that Fourier series is widely used in several of the main medical algorithms that interpret the wave functions that come out of your head. So, for instance, if you were an anesthesiologist, and I know there's at least one in the audience, you would be monitoring on a screen some data that comes from these electrodes to have one of several measures of how deep your patient is under anesthesia. And several of those use either purely the Fourier coefficients or a mixture of Fourier coefficients and the time domains to give the clinician something that's quickly interpretable in this high-stress situation of monitoring their patient in real time. Right, among other things, the epsilon and delta formulation of limits was driven by the drive to make Fourier theory rigorous, and so was Cantor's set theory, and also down at the bottom there, the so-called Calderon-Zygmunt theory. So a word about Fourier and his life. Here's an extremely abbreviated version. He survived the French Revolution. He became a student at the École Normale, which was a short-lived institution. In the revolution, he played a role on revolutionary committees in his town of Auxerre, and later on, he was imprisoned at least 4 times, by my count, and it's a little unclear whether this was for having been sufficiently revolutionary, too excessively revolutionary, or insufficiently revolutionary, or possibly both at different times. But yes, twice in Auxerre and twice in Paris, as far as I can see. But luckily, at one point, the fall of Robespierre happened at exactly the right time to avoid Fourier being executed, and so he was subsequently released from that imprisonment, and he lived a life close to the edge. After that, he returned to the newly formed École Polytechnique in Paris, but he was only there for a fairly short time when the French revolutionary government mounted the expedition to Egypt. And you may have been wondering why there's a picture of the Rosetta Stone on this slide. And it is because Fourier played an important, if somewhat tangential, role in the deciphering of the Rosetta Stone and also in the expedition to Egypt, which was an enormous undertaking. Over 100,000 personnel went on this 3-year expedition to Egypt from France. Hundreds of scientists, supported by soldiers and sailors and lots of other people. And they went collecting and finding out about the culture and the history of Egypt. And during the time that they were occupying northern Egypt, including a small town called Rashid on the near what is now near Cairo and Alexandria, a stone was found by French soldiers embedded in the wall of a fortress, 17th century fortress, and the stone turned out to be just over 2,000 years old and was from a much earlier temple stela, which had been put up in a different place further inland, and eventually moved somehow to this town, Rashid, also known as Rosetta. And that's where the Rosetta Stone was found as a piece of building material in a wall. They looked hard for the top part. It was already broken by then, but they could not find any other pieces of the stone. And as you may know, its importance is that it has, in 3 languages, hieroglyphics at the top, Demotic, which was a priestly script, in the middle, and Greek at the bottom, the text of an edict by one of the pharaohs, Ptolemy V, about various things. And it was this stone that made it possible to rediscover the meaning of hieroglyphics when it was eventually decoded in 1822 by a young man who called Jean-François Champollion, who, as it turns out, was not from where Fourier was then living, but somehow had moved to this town where Fourier was then living. Fourier had known him as a child, had encouraged him as a linguistic prodigy to take up the study of languages, and had told him tales of the expedition to Egypt. This young man became expert in many languages and was Champollion, who sometime later, along with or in competition with Thomas Young, an English polymath, interesting in his own right, who made some initial progress on deciphering the hieroglyphics, but it was Champollion who completed that task and who really worked out the phonetic correspondences of the hieroglyphics and realized, in fact, that it was a sound system. It's not just a picture script, it is a sound system. So, well, there you have it about the Rosetta Stone. the scientific expedition to Egypt was interrupted for military reasons when the English invaded the French-occupied Egypt in their turn. Are you following me? And the English allowed the French to keep some of their scientific materials they had gathered, but not the Rosetta Stone. So that is why you can now find the Rosetta Stone in the British Museum off the Great Hall in room 4. I encourage you to go. And so the French, including Fourier, returned to France in 1801. And then over the next few years, Fourier was responsible for pulling together the massive book called The Description of Egypt, which was 21 volumes, and he wrote the introduction to that. Well, there's more that can be said about that, but I will stop there. After that, Napoleon appointed him the prefect of Isère, which is the area around Grenoble in the southeast of France, and that explains why there's a map of Route N1, which goes from Grenoble to Turin over the Alps. And one of Fourier's many accomplishments was getting at least the first half of that road built as far as Briançon, and I think it was one of the first reasonable winter passages over the Alps. And that was one of several very important administrative things that he did. Of course, he wrote the analytical theory of heat. Later in life, he became the perpetual secretary for mathematical sciences of the French Académie des Sciences, but not before losing his job again and having no pension for a while, and etc. So anyway, I could go on, but I won't. But I strongly recommend Elena Prestini's book and also Tom Kerner's book, Fourier Analysis, and Elena Prestini's book on applications of harmonic analysis, which has a lot of biographical information as well. Okay, on to Calderon and Zygmunt. Zygmunt was a Polish mathematician who emigrated to the United States during or just around the time of the Second War. And Calderon was initially an engineer in Argentina. Zygmunt met him on a visit to Argentina and persuaded him to move back to the University of Chicago, where together they developed what became known as the Chicago School of Analysis or mathematical analysis. This is a picture of Calderon with his wife Alexandra Bello, who was a Romanian mathematician, well, still is, and she worked on ergodic theory and harmonic analysis, and is a very interesting person in her own right. And all three have biographical articles in the notices of the American Math Society, should you wish to find out any more about them. But here we come to the first of the math that's closer to what the main central part of my talk. And so the central type of question you'll see within this Calderon-Zygmunt part of harmonic analysis is you've got an operator, T, typically a singular integral operator, and I'll give examples in a minute. And it acts on one function space and from one function space V to another. So it takes in a function f that's in V, and it spits out another function T of f, which is in W. And the typical question you ask is this operator bounded from V to W? Or let's instantiate that with, is it bounded from L2 of R to L2 of R? So what would that mean if it were bounded? The quantity I have on the right here, the square root of this integral of size of f of x squared, where x is running on the real line, that's what's called the L2 norm of f. It's a measure of the size of f. And in physics, this particular quantity is often thought of as the energy of the particular function f you have. So f might represent a state of some physical system, and this number, real number, you get out, is a measure of the energy of that state. And so, if you like, what this question is asking is it always the case that for all possible states, for all functions f in L2, there's a universal constant c that doesn't depend on the function, so that the L2 norm of what's spat out, T of f, is less than c times the L2 norm of the original f. So it's saying, does, in a very quantitative way, does bounded input give bounded output? Is there a universal number associated with this operator so that it doesn't, it might increase somehow the energy of this particular state, but not by more than a factor of c. That's what it would mean for T to be bounded from L2 to L2. And the type of operators that we study include the Hilbert transform H, which Elias introduced in his talks on Tuesday, as he did several other things I'm going to talk about. A higher dimensional version of the Hilbert transform is the Riesz transform. A generalization of that type of operator is now known as the Calderon-Zygmund operators. You can also have commutator operators, where you are taking the action both of some T, which might be the Hilbert transform, and also of a function B times the identity operator, and applying the commutator of those two to a state. And there are several other types of operators that we study as well. The function spaces that they act on, this V and W in my picture at the top, could be the Lebesgue spaces LP for P equals 2, as I just said, or for some other value of P. So you just, everywhere you see a 2 there, you put in P could be 3/2 or something else. Also the Hardy spaces, which Elias also mentioned, HP. And then there are function spaces called BMO, which stands for functions of bounded mean oscillation, VMO for vanishing mean oscillation, weighted variance of these spaces, and so on. So why do we care about this question of whether a singular integral operator is bounded? Well, a lot of the early motivation came from partial differential equations, and I'm going to mention a few examples. One of the first such results was Calderon was working on the Cauchy problem in PDE, and PDE problems have problems about existence of solutions, smoothness of solutions, and also uniqueness of solutions. Does the problem have a unique result? And he found that he could prove a uniqueness result for the Cauchy solutions of the Cauchy problem using a new kind of inequality, a so-called pseudo-differential inequality, that gives bounds on two singular integral operators, P and Q, that show up somehow in his proof. And it's a little technical, and I'm not going to show you the details. It did extend earlier uniqueness theorems due to Cauchy and Sonia Kovalevsky and to Kalaman. But let's move on to a more concrete example. This one's important historically. But why do we care about integral operators at all? Well, let's say here's probably the simplest ordinary differential equation we might want to solve. My code is that blue stuff is stuff we know, and red stuff is stuff we're looking for. So our differential equation for some unknown function u of x that we want to find is its derivative is equal to some known function f. So I might just tell you f of x is x squared. What's the u whose derivative is x squared? You would all say 1/3 x cubed plus a constant if we're lucky. Okay. So that one you can solve, but what did you just do? You integrated x squared. So that's why you want an integral operator, because it undoes the effects of differentiation that are showing up in your differential equation. Okay, fine. Here's another example. Here's a second order ODE, the driven harmonic oscillator. Again, we've got some known function f, which here represents the driving force you're applying to your system. And here you've got the, well, what would be the simple harmonic oscillator equation if you weren't driving it. And you're setting some particular boundary values so that at the left-hand end of this range of the input variable, your u is set to be 0, and its derivative is kept at 0 at the left-hand end. And it turns out, so many of us have solved this equation in many different contexts, including teaching our DE students. But if you mess around a bit with the solution, you'll find that you can write the desired solution u in this form. It's an integral where you're multiplying the known driving force f by some other function and then doing the integral. And this other function you're multiplying it by we call a kernel, and that kernel, often called k of xy, in this case it has some signs in it, comes from the exact form of the differential equation together with the boundary conditions. So if we had a different differential equation and boundary conditions, we would have a different function as the kernel. Okay, so again, we can find the unknown solution by integrating the product of the known driving force with this kernel. So this is another integral operator. What we're doing is taking f and integrating it times something else. Okay. Here's another example where we have a slightly more complicated differential equation, the sum of all the second derivatives in the upper half plane, including time kind of on the vertical axis. And here the unknown function is given as the boundary values. So this is called the Dirichlet problem on the upper half space. We want to know, in words, what we're looking for is a function u that is harmonic everywhere on the upper half space and has given boundary values on the boundary of the upper half space, which is a copy of Rn. And here we have the same type of formula for the solution. Our desired solution u we can get as the the given data f multiplied by a different kernel, in this case one called the Poisson kernel. And in this case you can see that the kernel has a singularity. So if your x and y and t, if your x was equal to y and your t were 0, you'd be dividing by 0, and they take away your mathematician's card when you do that. So there is a singularity in there that you have to deal with, and this is the type of kernel you get when you're dealing with a singular integral operator. The kernel has got some sort of singularity, and there's a huge range of different types it could have, but it could have them. Okay, so the last one I'm putting in just for Irina, really. So in the kind of PDE and complex analysis that she works on, you could have this same type of Dirichlet problem where you're looking for a harmonic function, but the boundary of your domain is no longer a nice flat half space or plane. It's quite rough. So it could have some Lipschitz regularity or something, but you're trying to solve this problem in the upper half space, but above some kind of rough surface. And then you have a more complicated kernel, which ultimately you can get down to the desired solution u is the known boundary data f, operated on by this inverse of some operator and multiplied by some other kernel here and integrated over the boundary. And it turns out that I'm told what this comes down to, being able to know that this process will work and this integral converges, is you need to know that to invert this operator, half of the identity plus t, it has to be, if you know that the t is bounded, that's an important step in showing that this operator is invertible and therefore that this whole thing makes sense. And so there is a singular integral operator t in here, and you need to know that it's bounded. Okay. So there's lots of PDE motivations for studying these types of questions. Now, excuse me. Let's go back to those building blocks. So down here, I've got a wiggly function like I showed you at the start, broken into its two sine and cosine type building blocks. And I've got an example of another function broken into Haar wavelet building blocks. And then I've shown you another kind of wavelet building block. This one is compactly supported on this section, so it's 0 before and after this. But you can see it's more continuous than the Haar wavelets. It doesn't have any jumps. And there are versions of these wavelets that have as much differentiability as you want. You can make a version that's 10 times differentiable or whatever. These were discovered by Ingrid Dobeschi, pictured above there. And so these have been extremely useful in many applications. And then there's also a fourth type of wavelets developed by Pascal Aucher and Thomas Huttinen, which we've used in our work, but I haven't drawn any of those. So these are the type of building blocks. Here I'm just talking about how you actually compute the coefficients, so I think we'll skip quickly past that. I've mentioned more of the types of operators that we are interested in studying, including a formula for the Hilbert transform. But I just want to wind up this little section with the selected elements of the Calderon-Zygmund theory. So the type of things that you try to prove in the Calderon-Zygmund theory, I will list some of them. There's an interpolation theorem that says if you have one of these nice operators, singular integral operators with some nice properties, that are bounded on L2, then you can conclude that it's also bounded on other function spaces, namely all LPs, all the way down to p equals 1 and all the way up to p equals infinity. So this is a useful thing to know. You get sort of more boundedness on more function spaces for free. The T of 1 theorem gives some checkable criteria for when an operator T is bounded on L2. So if you get the answer yes from these criteria, then you know that you're there. And this is what one of the projects my student Trang Nguyen is working on, is a generalized T of 1 theorem in a much more general setting. There are half functions, and they form an unconditional basis for LP. There is a Hardy space H1, and there are other versions HP. You can define these Hardy spaces in various ways in terms of atomic decomposition or other things. There is a space BMO, space of functions of bounded mean oscillation, which turns out to be the dual of this Hardy space H1, and this H1 is in turn the dual of another space of vanishing mean oscillation. Oops. And then there are a number of other theorems. There are relationships between discrete and continuous versions of these function spaces, and that's something that I've worked on quite a bit. There are various averaging things you can do. There is a Calderon-Zygmunt decomposition. There are more interpolation theorems, and so on and so forth. So I just want to give you the impression that this is an enormous part of analysis. There's lots of results. We kind of know how it all fits together. And what my group and many others have been doing is extending all of this, and we've succeeded in generalizing much of this from the situation where our function spaces consist of functions whose inputs are real numbers or at most real vectors, which is the classical case, to the situation where the functions we're dealing with in these function spaces are defined on a much more general set. X. So what is X? Let's look at that now. So change of pace at the beach. We've had enough of Cambridge. We've gone to some nearby beach. Oh, I forgot to ask the name of a plausible nearby beach, but just imagine yourself on the beach of your choice. And you have a beach ball. And there's a few ways you could measure the size of the beach ball. You could ask for its volume, three-dimensional volume. You could also look at the two-dimensional size of its shadow down there on the beach. Okay, now let's double the radius of the beach ball. What happened to its size? So its volume increased by a factor of 2 to the 3, right? Its shadow increased by a factor of 2 to the 4, 2 to the 2, 2 to the 2, right? Okay, so depending on what sort of dimensional type of measure we were using, we are getting a different factor. But the point is that the quantity we were using to measure the size of the ball, when we doubled the radius, the value of that quantity increased, but only by some specific known amount. And it turns out the key feature of that is that the volume of the ball of twice the radius is no more than, in our case it was equal, but bear with me, is no more than some specific constant, for n-dimensional volume it's 2 to the n, times the volume of the original ball. So the words we say about that are that the volume of the ball is what's called not just a measure, but a doubling measure, which means exactly that. If you double the radius of any ball, wherever it is, whatever size it was, the volume of the new ball is no more than fixed constant times the volume of the old ball. And it turns out this is one of the key features of Lebesgue measure that makes all the classical proofs go. So this was one of the insights about what are you really using when you prove all those things on the previous slides, 2 previous slides. This is one of the key things you're using. Now, in a space of homogeneous type, instead of, it's a triple, so instead of the real Euclidean space Rn, we just have a set X. We're going to have much less structure. Instead of the Euclidean metric, we're going to have a way of measuring distances between 2 points, which is just called a quasi-metric. It's not even as good as a metric. So it's like a metric in that the distance from A to B is the same as the distance from B to A, and it's 0 if and only if the points coincide. However, we don't have a triangle inequality. We have a substitute called the quasi-triangle inequality, where the distance from, let's see, A to C is no more than 10 times the distance from A to B plus the distance from A to C, for some universal constant 10 that works for all pairs of points or triples of points. Okay, and the other piece of kit is, instead of Lebesgue measure, think volume or area, you have a doubling measure that has this property that I just described. Okay, so in harmonic analysis in the 30s, complex methods were extremely important, but we these days are using other methods as well, including real methods, and changing the domain to these spaces of homogeneous type. Okay, so I want to just give you a few examples of these spaces of homogeneous type, which are wildly varying. Perhaps some of your favorite spaces are here. Perhaps you like the Heisenberg group, the boundary of the unit ball in Cn, or perhaps you like the four corners Cantor set, or compact Riemannian manifolds, Riemann surfaces. All of these are spaces of homogeneous type. And here are pictures of some of them. So they can be disconnected. They could be the graph of a Lipschitz function. There are some discrete examples that have surprising properties, which I will skip all of. Compact Riemannian manifolds are spaces of homogeneous type. If the manifold's not compact, this is what happens. This is made in crochet. It's a hyperbolic surface. It's a non-compact Riemannian manifold. And if you study it for a while, you'll come to the conclusion that because of all this growth of the matter, the unit balls measure, the ball of radius r measure scales like an exponential in the radius, and therefore it turns out it can't be a doubling measure. So this is not a space of homogeneous type. Okay, the beautiful math of coral in the crochet coral reef will take you further in that direction. But the point is, we've thrown away almost all our structure. We have no zero, we have no coordinate directions, we have no addition, we have no Fourier transform, and yet we can still do a version of this Calderon-Zygmunt theory that I spoke about. So I am going to zip through, well, I'll just say the point is that we've built a theory where our function spaces can consist of functions that are defined on any of these crazy spaces X I've been talking about. Their outputs, for simplicity, are still just real numbers, but their inputs have become wildly varied. And in this situation, we can reproduce that Calderon-Zygmunt theory that I summarized for you before. So I'm going to actually not tell you anything about my part in this, as it turns out. There are a lot of things that you have to generalize that don't work out very much the same way. The only thing I'm going to say is that okay, so here's just one example where we're trying to define a particular version of one Hardy space, in this case, the dyadic version of the Hardy space H1. And the way we're going to do that is it's going to be the integrable functions whose square function satisfied is also integrable. But what that comes down to is a summation condition that says the sum of these double Haar coefficients. So now I'm in a product situation, so it looks much more scary, but just as I took the single Haar coefficients of f in a product with some Haar function before, on the first slides, here in this case I have a double Haar function. But what this terrifying quadruple sum comes down to is a summation condition on the size of these double Haar coefficients. And this is the right one to give us the right generalization of the classical Hardy space. So there is much more that we could say, but I won't. But what I will just close with is some insights. In particular, we and many collaborators have, and many researchers have succeeded in generalizing a lot of this theory to the situation of spaces of homogeneous type. In particular, an important contribution, I think, is that we explicitly construct a Haar basis on each of these crazy spaces that I just mentioned. So that's not so hard on the real line. You just have a function that goes down for a while and then goes up for a while, and you scale the height so that it's in L2 norm is 1 and you're done. But in one of these very floppy spaces, it's a much harder task to figure out what are going to be these basic building blocks. And we have written that down carefully. The ultimate dream here, I think, is to try to build a theory of partial differential equations for functions whose inputs come from these spaces of homogeneous type. And there are already quite a lot of steps in that direction, and some people in the room have contributed to that effort. So it's not so clear what that means physically, but I think it will bring understanding and ultimately applications, as maths tends to do. But what I will close with is a very short word from our sponsor Fourier, from the same introduction of the same work. And what he says is, mathematical analysis is as extensive as nature herself. It defines all observable relationships. It measures time, space, force, and temperature. This difficult science grows slowly, but once ground has been gained, it is never relinquished. It grows without ceasing, in size and strength, amid the constant error and confusion of the human spirit. That's what we do. Thank you.
What's the situation with the non-spaces of homogeneous type? If you relinquish even the doubling condition on the measure?
Yeah, great question. So what if we have something even weaker on the measure? So there has been quite a lot of work on that, and in fact Trang's T of 1 theorem is in a yet more general situation. So one thing you can do is allow the measure to be not itself doubling, but to be bounded above by a function which itself is doubling. So these are called upper doubling measures. So Huttunen and collaborators, Martikainen and many others have worked there, and you can recover a lot of this, amazingly. Yes, I could talk more in detail later, but yes, there are some results in that direction. So it was thought for a long time that doubling measures were the last words, that was the key property, but there's a famous paper of Juan Verdera called The Fall of the Doubling Measure, where he talks about some of the stuff that has come after that.
One of the historical perversities is that the discrete Fourier transform was known 40 years before La theory by Euler, and the fast Fourier transform was formulated by Gauss 15 years later, but was published only in mid-1840s.
Yes, yes. So again, there's a history of rediscovery and of aspects and of things that were discovered whose application or connection was not perceived at the time. And I left out the part about people's work not being properly examined, reviewed, published, cited, etc. But yes, it's a tangled history.
In a nutshell, what is the share of Huttunen wavelength?
So what they do is first of all, there's a construction of dyadic cubes on these spaces of homogeneous type, which is a story in itself. So instead of taking a cube and cutting it in 4 and then in 4 again and then in 4 again all the way down, there's a much more complex construction, which is necessary because the spaces are so floppy. But then you have a natural subset of a collection of subsets of the space of homogeneous type. The way they construct the wavelet is as they construct an orthonormal basis of spline wavelets. So they build splines, iterated splines on starting with characteristic functions of these cubes and convolving them with themselves. So that's sort of technically how they build it. They establish that they have some Hölder decay properties and things like that. But the key point is that their wavelets, like the sines and cosines and other ones I've mentioned, can be shown to form an orthonormal basis for L2 on the space of homogeneous type, or for LP, or for the other functions that we're dealing with.
Another question.
fascinating tour of this area of mathematics. And you're all invited to stay around for some refreshments afterwards.
Thank you.